In this video, we are going to talk about the regularization of the linear regression algorithm. See, when we talk about the loss function of this linear regression algorithm, one of the common loss function that is being used, that means wherever the data that we have got is being fit on an algorithm, this x and y is being fit to my linear regression algorithm. It is being fit to the equation of y is equal to theta naught plus theta 1 x1 plus up to theta n xn. Now the goal is to find the values of theta naught, theta 1, theta 2 up n such that when I input the value of x, I'll be getting the output of y. Now, in order to reach the best values of the theta naught, theta 1, theta 2 up to theta n, in order to get the better values of the same, here the system is going to make use of what we call it as a loss function. Now, one of the commonly used loss function is the squared error loss. It's the squared error loss. So, for this squared error loss value, okay, by referring to this value, the system is going to decide as, okay, how it has to update the values of theta. So it will find the values of theta naught, theta n such that yes, this squared error loss is minimum. Now what happens is, in some scenarios, even though we use the squared error loss, in some scenarios the performance of the linear regression algorithm might not be as effective as we would expect. In such scenarios, we would see that even though like we have tried to find the best parameters, but the value of loss is very high. In such cases, what we do is we are going to apply the regularization for this linear regression algorithm. Now here, when we talk about this regularization, there are three types of regularization that are actually applicable in the scenario of this linear regression algorithm. The first regularization that we have is the Lasso regularization. And here in this Lasso regularization, which is also known as L1 regularization, we are going to add the constant values. Yes, we are going to add the parameters itself, okay, which will be the absolute magnitude of the coefficient as the penalty term to my loss function. So I'm adding an additional penalty term for my loss function. So in case of this Lasso regularization, the equation or the overall idea is something like this. Okay, the overall idea is for the Lasso regression loss function, the goal is to find the minimum value such that the squared error loss term, I'll say squared error loss plus lambda into absolute value of this theta. So this is the overall representation of this Lasso loss function. See, the idea is this squared error loss is what we have, that finding the minimum of squared error loss. It is the general loss criteria that we use it whenever we are performing the fit with the linear regression algorithm. Now on top of that, I'm going to add the absolute value of the magnitude of coefficient. Now here, what I'm trying to do is I'm going to multiply it with the lambda. So this lambda is another hyperparameter where I can tune this value to decide as how much effect that I need to have from this L1 term. Okay, if my lambda is equal to 1, then that would mean that I'm adding the absolute value. And if I say lambda is equal to 0, that means I'm actually removing this term itself, which is equivalent to linear regression algorithm. If I say lambda is equal to 0.5, then I'll multiply the absolute sum of values, whatever I'm getting, by 0.5. Now by applying this Lasso regularization, so what this would tends to do is this is going to tend to make the coefficients to absolute 0. Now you might be wondering as how does it make it absolute 0? See, just think about it. Okay, so here in this case, you have the value of loss function, that is squared error loss, and along with that you also have the term which says as absolute value of theta. Okay, this is what we have got. Now what is squared error loss? Squared error loss is y minus y hat whole square. What does y hat is made up of? Y minus, I would say, theta naught plus theta 1 x1 up to theta n xn. So this is the squared error loss that we have got. Maybe I'll have it as squared, something like this. Okay. So here, if you consider the squared error loss, I've got the parameters theta naught, theta 1, theta 2, up to theta n. Okay. And along with that, I have the additional term. Now, since I have the additional term, let's illustrate it with a very simple example. Let's say the general value of loss that I'm getting is 5000. Now, when I perform the addition, that is when I perform the summation of the absolute values of coefficients, I'm getting the value as another 1000. So now in case of L1 regularization, I'm getting the total loss as 6000 because 5000 plus 1000. Now 6000 is the outcome of sum of squared error loss and the absolute, yes, and the absolute sum of the absolute magnitude of these parameters. Now in such scenarios, yes, in such scenarios, if I want to reduce the value of loss function, I will be forced to reduce the value of coefficients. But the reason, because see, y is given from the data, x is also given from the data. Only the parameters, that is theta naught, theta 1, theta 2 is the one that is in under my control to reduce the value of loss, which in turn forces my algorithm to reduce the values of these coefficients furthermore. So when we are applying this L1 regularization, it actually tends to make the coefficients to absolute zero. The reason, because we are going to add the absolute value of magnitude. So here, in case if I want to apply this lasso regularization, so I can just import the model from sklearn.linear_model. I'm going to import lasso, and I can initialize my lasso regularization algorithm, that is the regression algorithm. And here for this lasso, I can also control the value of lambda that I had shown in the equation. So there are various parameters in this lasso, so we can actually go ahead and check out the same. So here the value of alpha is something. So using this value of alpha, we can decide as how much importance that I have to give for the summation of the parameters. Okay, by default it is set as 1. Okay, now I can go ahead and perform the fit on my training data, xtrain comma ytrain, and after I perform the fit, we can generate the prediction on the test data. Once we generate the prediction, so this time I'll just calculate the R2 score. So if I calculate the R2 score, the R2 score is 0.9122, which means with the application of lasso regression, so the overall R2 score, that means the explainability of the features about the target is still the same. Maybe I can fine tune it by changing the values of alpha. So we can either fine tune it and see whether we would get a better performance on this given data or not. Okay, now this is about the L1 regularization, and in the same way we also have L2 regularization. Now this L2 regularization is also known as ridge regression. Now in the scenario of this ridge regression, what we do is we are going to add squared magnitude. See, we are going to add the squared magnitude of coefficients as penalty term. So here, when we are adding this squared magnitude of coefficients as the penalty term for the loss function, what this is going to result is, this is going to result in getting the value of coefficients closer to 0, but yes, it is going to never, okay, never set the value of coefficients to absolute zero. So this is something that you need to remember. Now, when it comes to this regression, you can think of it as, instead of absolute value, you'll just take the square of it. That's all, team. So when it comes to the implementation, coming to the implementation is very simple. We'll just import the ridge regression, okay, and we'll initialize the same. And if I calculate the R2 score, see, with this ridge regularization, I'm getting the same output like before. Now, apart from this lasso and ridge, we also have another regularization technique that is called as elastic net regularization. In this elastic net regularization, it is the combination of L1 and L2. Okay, it's a combination of L1 and L2, where in this case we are going to specify how much L1 regularization that I have to apply, and then how much L2 regularization that I have to apply, and this we can control it with the help of the parameter. And this regularization method is called as the elastic net regularization method. So I'm going to apply it on this given data set. So I'll initialize my elastic net, and if I perform the fit, so we are getting the similar performance as we have got earlier. So for the elastic net regularization, we have the L1 ratio and the alpha. So with the combination of L1 ratio and the alpha, we can actually apply how much L1 I should apply. That it means how much L1 regularization to be applied on my given data set, and how much L2 regularization to be applied on the data set. So this is the importance of regularization techniques in case of the regression task. Now, we will revisit the topic of regularization even when we are talking about deep learning. So during the deep learning, we also can add the regularization methodology over there in our deep learning neural network, which will also help us in preventing the overfit in the deep learning neural network. Okay, so this was about the regularization methods of linear regression. Moving on, the next topic that we have got is assumptions of the linear regression algorithm. See, when we are applying the linear regression algorithm, at that time, we have to ensure that the data set that we are using, it actually follows the assumptions of this linear regression algorithm. It is our responsibility to ensure that the data that we have follows the assumption made by this algorithm. If the data does not follow the assumption, then at that time there's a very high chance that my model would not work as per our expectation. Hence, it is our responsibility to ensure that it satisfies the assumptions. So the first assumption that is being made in case of linear regression algorithm is there is a linear relationship between features and the target. So here in my given data set, so let me just bring back our data set. In our given data set, the features are TV, radio, and newspaper, and the target is sales. So the first assumption is there is a linear relationship between them. So how do we check for linear relationship? Well, we can check for linear relationship by creating a pair plot. Okay, so I can create a pair plot which will be a scatter plot for my features and the target, which will help us to visualize whether we have the linear relationship between the feature and the target or not. So import cmos sns dot pair plot. Here df and x variables are TV, radio, newspaper. So I have mentioned my y as sales. Now if I create a plot, see, this is how the plot would look like. As you can clearly see, there is a kind of linear relationship between my TV and sales. Okay, and there is a loosely linear relationship between the radio and sales. And I would say that the between the newspaper and the sales, So there's not much of high a positive relationship or positive linear relationship between newspaper and sales. Okay, that is what that we can clearly observe in the scenario of this case here. In this case, that is the pair plot. Now this is a visual method. Now apart from that, if I want to go ahead and look into the numerical method, so we also have a Pearson correlation coefficient. So I can create a matrix like this. I'll say df.corr, which will help me to get the correlation coefficient correlation coefficient between the variables. So here I'm interested in the sales column. So TV and sales are having the correlation coefficient of 0.78, radio it is 0.57, and newspaper you can clearly see it is very low, that is 0.22. Okay, so in this way we can visualize the data. Now another important assumption that my linear regression algorithm is going to make is there is actually a mean residuals. The mean residuals of my given data set is actually equal to 0. Okay, the mean residual is actually equal to 0. So this is another assumption of this linear regression algorithm. So let's do one thing. Let's go ahead and generate the prediction for this given data. So here we have the YPRED test. See, I have the YPRED test. Now, if I calculate the mean of this YPRED test, that is the difference between Y and YPRED test. So let me just calculate the residual. See, residual is given by, okay, Y test minus YPRED test. Okay, this will be the residual. If I now display the residual, this is the value of residual. Now, if I calculate the mean of this residual, see, I've got the value of mean of this residual is minus 0.075, which means it is closer to 0. So the mean residual in this case is closer to 0, and I can say that for this given data set, this clearly satisfies the assumption of this linear regression algorithm. Okay, and the other technique, other assumption that it makes is there is a normal distribution of error term. So we would assume that there is a normal distribution of error terms. So whenever we want to look into the distribution of any given data, we can easily make use of this plot to look into the overall distribution of this data set. So if I say residuals and plt.show, so this is how the plot would look like. Okay, so this is how the overall plot would look like. We can clearly observe that there is a normal distribution of the error terms. And another condition that we have got, or another condition or another assumption that we have got when we talk about this linear regression is multicollinearity. So here in the scenario of this multicollinearity, what happens is we will make use of the statistical term that is called as VIF score, or the variance inflation factor. Now using this variance inflation factor, we would actually find whether there is any correlation between the features or not. See, we are okay to have a high positive correlation or high negative correlation between my feature and the target, but we do not expect the features to have the correlation between each other, and that is called as a multicollinearity. So whenever the data that we have got is having the multicollinearity, at that time the ability to generate the prediction is going to reduce. The reason because, just think about this with a very simple example. Let's say in your data set you have got height, weight and BMI. Now the expectation is, using this height and weight, you have to predict the BMI score. Now one thing that you would find is, okay, if the height increases, BMI is going to increase, weight increases, BMI is also going to increase. But there is a very high chance that if I increase the height, then the weight is also going to increase. In other words, if I'm analyzing the individual column, let's say height, and if I increase this column, even though I want it or not, this is having an effect on weight, which actually creates a confusion for the model as whether this change in BMI is due to height or whether it is due to height. So the predictive power of my linear regression algorithm is going to decrease whenever we have got the multicollinearity issues in the given data set. Now to check for the multicollinearity, we will make use of variance inflation factor. So in order to find this variance inflation factor, we make use of the library that is stats models. So I'm going to say from stats models dot stats dot outlier underscore influence, I'm going to import variance inflation factor. Okay, it says that there is no module found. So here to do the installation, so the command that I have to run is pip install stats models. So let me just include this command in my notebook so that during the execution you can do the installation first. Okay, so this will take care of the necessary installation. Now once it's done, we'll just come down and we'll try to import the same variance inflation factor. Okay, so here once we have done the import, in order to calculate the variance inflation factor, we have to send in the data, and also we have to send in the column index for this variance inflation factor function. So in order to find the same, I'll start by defining my own custom function. I'll say def VIF score and I'll get the data that is X, and here whatever the data that I'm going to get, let's say I'll be sending the data which is in the pandas data frame format. So I'll extract it in the format of an array by getting the values attribute. Next, I'll calculate the VIF score as variance inflation factor. Here for this function, I'm going to specify X and Y, where X and Y are nothing but X is my array that we have got earlier. I'll say X array. Okay. And here for I in range, I'm going to say X dot shape number of columns in my data set. Okay. Now once this is done, I'm going to create a pandas data frame, pd dot data frame. Okay, I'll just mention it like this. Next, for this data frame, I'm going to add a column called score, which are nothing but my VIF underscore score. Then I'm going to add the column for my data set. So I'll say VIF score and I'll mention a new column called features. This is equal to X dot columns. Okay, then I'm going to return. So here VIF is equal to VIF. Okay, I'm going to return VIF underscore score. So in this way, I'm going to create a function. Now for this function, I'm going to send in my xtrain. I can send in my xtrain. This will help me to calculate the VIF score on my given data set. Okay, I have in the given example, I've actually sent in my xtrain, or instead of xtrain, you can also send the x as well. So if I send in my data set, this gives me the value of variance inflation factor. So the way that we interpret is, if I have a VIF score, okay, the general thumb rule, if I have the VIF score greater than 4, then that means there is a multicollinearity in a data set. So if the VIF score is less than 4, there is no multicollinearity in this given data set. Okay, So it's not so it is not zero multicollinearity, but if it is less than 4, I would say it is negligible or moderate multicollinearity in this given data set. So when we have multicollinearity in a data set, what we do is we are going to drop the column which has the highest multicollinearity value, that is VIF score, and we repeat the process of evaluation of this VIF score. Okay, so this was about the assumptions of linear regression algorithm and the regularization technique that will be applied on the linear regression algorithm. So from the examination perspective, you need to be remember about what is the overall assumption of this linear regression algorithm, the way in which the data will be fit for the given data set, that is between x and y, and some of the assumptions and the way in which that we evaluate the linear regression algorithm. So team, with this we come to the end of this video. We'll continue further in the next video where we will take a look into the another algorithm which comes under the classification, that's called as the logistic regression algorithm. So I'll see you next time.